in pursuit of transferring technical knowledge and just to gear up for the new engineering entrant, myself Pranav is here to deliver today's presentation, Power Transformer Part 36. As the topic is of the continuation, so for your convenience, the link of the previous one is given under the description box. Let's start with transformer tappings and tap changers basic principles. The coordination between the power generation and the pattern of power consumption in local power grids is extremely complicated, as because the loads and currents both are constantly varying in the grid system. Voltage fluctuations are thus to be inevitable in the network with the change of load current in the transformer winding. But the power transformer is always be designed to work within a range of steady state voltages and be capable of withstanding the voltage fluctuation within a certain range. The permitted fluctuations is to be determined by fluctuations in the source voltage and the loading current, and that fluctuation has a direct influence on the transformer's dynamic responses by causing a change in core vibration. The power source variability would have to influence the voltage fluctuation in the transformer circuit, and that also leads to change in transformer loading status. Technically speaking, the stability of the voltage is one of the prime indicators for determining the power quality of the connected grid. The excessive voltage fluctuation would have to affect the user's normal operational activity, as because it is not at all conducive to have safe and economic operation of the power system. Once the voltage becomes too low, then the network loss must have been further increased due to increase of load current, and that may even damage the stable operation of the system. Or otherwise, if the voltage is too high, then that will directly intend to pressurize insulation level of the load side electrical equipment and also force to generate the corona loss in the high voltage network. For better coordination, the transformer voltage at the load side has to be made as close to the design value, and this can be done by adjusting the voltage ratio with certain addition or removal of tapping turns. Taps are the connections provided at various points on any of the windings, primary or secondary side, where the turns ratio differ from one tap to another, and hence different voltages can be obtained at each tap. For an in-service transformer, provision of taps has made the system more convenient of maintaining the appropriate magnetic flux levels in the transformer to sustain its rated secondary output voltage. So, tap is a direct connection to a turn on a transformer winding at a voltage other than the normal rated voltage, which changes the voltage ratio in such a way that its secondary output voltage stays at nominal rated voltage. Now, provision of taps are essential for the purpose of one, the power supply authorities, as they are always be liable to maintain the supply voltage between certain limits. So, a device like tap changer is fitted to power transformers for regulation of the output voltage to required levels. Number two, variation of voltage as corresponds to change in load can be adjusted by the application of tap changers, which would have thus to facilitate a variable control so as to keep the output voltage within the prescribed limits. Taps are being facilitated to maintain requisite magnetic flux levels within the active part of the transformer so as to provide the transformer's rated secondary output voltage. Number four, on generator transformer and interbus transformer, provision of tap changers are rather to assist in regulating the system var flows so as to control the real and reactive power. Taps are provided at HV windings of the transformer because of the following technical reasons. Number one, the number of turns in the HV winding is much larger, and hence a fine voltage variation can be obtained with wider range of voltage regulation. Number two, for large transformers, since the currents at LV winding are being considerably much higher than that of the HV winding, so any sort of interruption on high currents is always be a difficult task. Number three, as of the winding construction, LV winding is placed adjacent to the core surface, whereas HV winding is physically wound over the LV winding and is kept on the exterior side because of insulation consideration. To provide taps on the HV winding is being comparatively easy accessible than that of the LV winding. Number five, during at light loads, in case of step-down transformers, the LV side voltage would tend to increase, and it requires to decrease this voltage by adjusting the taps on HV side where number of turns are large. Number six, as being with large number of turns HV side winding, the flux and flux density would thus to be decreased, and that leads to have a significant reduction of core loss, which may have to enhance the transformer efficiency at light loads. Provision of taps that are to be implemented only on one winding, whose number of turns would thereby be changed to maintain a constant voltage configuration in other winding, while the number of turns in other winding remains same. Such phenomenon would have to create unbalance in the magnetomotive force as introduced within the active part of the respective transformer, which leads to produce magnetic asymmetry in axial direction. 9. Severe mechanical forces might have been the resultant effect of this type of magnetic asymmetry, causing massive displacement of the winding in axial direction. Transformers equipped with taps are not only costlier, but also much more problematic with great internal complexity and less reliability as compared to transformer without taps. Number 11. Multiple tapping points may have to accommodate and supply different voltage levels as per circuitry requirements, despite their certain drawbacks. Location of taps. Number 1. Depending on transformer constructional features, the taps can be provided either at the phase ends, at the neutral point, or in the middle of the winding. Number 2, transformer having with limited cover space, it is always be made advantageous for providing taps at phase end, as because required bushing insulators would then be reduced in numbers. Number 3, if taps are provided at the neutral point, then the insulation between the various parts will obviously be reduced, and such type of configuration is comparatively economical, particularly for the high voltage large transformer. If large voltage variation is required, and thus to restrict magnetic asymmetry, then taps are to be placed near the center of the winding. However, such configuration can never be applied on low voltage winding placed next to the core. Configurationally, taps are to be denoted as principal tap position is denoted, at which the rated secondary voltage can be obtained for the rated primary voltage. Positive taps and negative taps are thus to be denoted as the positions above or lower of the principal tap respectively, and at those taps where the secondary voltages are to be maintained higher or lower than that of the principal tap position. As the power capability of the tapping is equal to the rated power, so at the positive taps, where the rated current for the tapped windings must be reduced, and subsequently at the negative taps, the rated current for the tapped windings must be increased, vice versa. Now, provision of taps would perhaps initiate some sensitive phenomena which may represent a significant source of unreliability. A. If the number of turns of the primary would have been fixed, then the flux density B in the core is directly proportional to the ratio of V by F, where V is the voltage and F is the frequency. That is, B is directly proportional to V by F. B. So, case of overfluxing in transformer would have been resulted with an increase in supply voltage or decrease of supply frequency. With the provision of taps and by operating the tap changer, if the number of turns would be reduced to enhance the secondary voltage, then the flux density in the core must have to increase. Hence, while designing the transformer, designers should always be careful to have provisions of suitable margin of increase in the flux density due to tap changer operation or tap changing operation. E. The margin of allowable increase of voltage and decrements of the system frequency both are also to be seriously taken care of. If it has been exhibited that the extent of overfluxing occurrence is relatively high in step-up transformers in power stations compared to step-down transformers in substations, where voltage frequency usually remain constant. While in carrying load, the transformer's secondary voltage would thereby to diminish by an amount which is determined by the transformer's impedance and the power factor of the load, that is load power factor. The load and its corresponding power factor as would have to vary, and accordingly the output voltage also to vary. To make the voltage within the acceptable limit, the desired voltage regulation is made possible through the use of a tap changer. Now, case of overfluxing in transformer would have been resulted due to underneath occurrences. One, increase of supply voltage as due to sudden load throw off. Number two, the receiving end voltage of a very long AC electric power transmission line would be more than the sending end voltage due to the Ferranti effect if the transmission line is lightly loaded. Most important. At the time of restoration transmission line, after shutdown work, the switching process during the energization is also one of the major causes which creates over voltage surge. During this phase of restoration, transient voltages or switching surges are caused by energizing large segments of a transmission system or by switching capacitive elements. Transient over voltages are usually be a significant factor at the long transmission line of voltages above 400 kV. Number 6. Such overvoltage criteria may put the transformer into saturation, causing core heating with excessive harmonic current generation. Number 7. Shunt inductive compensation method is applied to either during the time of charging the transmission line or having very low load at the receiving end where a very low current flows through the transmission line. Shunt inductive compensation method is applied. Now, as of the shunt capacitance in the transmission line, that would have to instigate significant amount of voltage amplification, that is due to Ferranti effect at the receiving end. Just to compensate it, shunt inductors are connected across the transmission line. Whenever an inductive load is connected to the transmission line, the power factor would have to lag because of lagging load current. Number 11, to improve the power factor, a shunt capacitor bank is thus to be connected in transmission line, which has to draw current leading to the source voltage. Number 12, shunt capacitive compensation unit as connected to transmission line. If it is not properly designed or executed, then there may be a chance of overfluxing at the associated transformers. To allow overfluxing for a longer period that may lead to damage the core of the transformer. Number 14, the tap change itself represents a significant source of changing in leakage reactance, I square R loss, and core loss. Transformer tap changer. Transformer is a device which has to transform the alternative current and voltage between high voltage and low voltage windings, keeping the power capacity same. The power transformer, while delivers the voltage at constant variable conditions, then the variable number of turns on the power transformer would have to be selected by using tap changer. The basic concept is so far been established that the system voltage regulation can be subsequently controlled while the steady state voltage will be at an acceptable range in transmission line system. Voltage stability would thus be controlled by using tap changing transformer. The transformer tap changers are of two types. One, on-circuit tap changer, that is OCTC, or on-load tap changer, OLTC. Number two, off-circuit tap changer, OCTC, or de-energized tap changer, DETC. Most of the power transformers above 10 MVA rating would have been recommended for incorporating on-load tap changer as a means of voltage regulation. Since the transformer will be in energized condition with carrying load, so the switching principle of OLTC arrangement would have to follow the make before break contact concept. However, OCTC and DETC arrangements are preferred mainly in high voltage distribution type transformers where no load tap changing concept is applied on the primary winding for just to accommodate transmission system voltage variations within a narrow band around the nominal voltage rating. On-load tap changer, that is OLTC. Higher capacity transformers equipped with OLTC, on-load tap changer, have been developed to provide maximum reliability in operation where HT side voltage variation is frequent and a nearly constant LT voltage is required. The concept of introducing OLTC for regulating the power transformers as corresponds to electrical energy networks and industrial applications would obviously be stated as a major breakthrough in enabling the voltage regulation and or phase shifting by varying the transformer ratio under load without interruption. The main function of OLTC is on the principle to change the tapping section or tapping connection of a winding while the transformer is under load. On-load tap changer will therefore continue to play an essential part in the optimum operation of electrical networks and industrial processes. Major components of OLTC is shown in figure 126. See the diagram, elements on on-load tap changer. Tap changer, according to the principle of operation for ensuring uninterrupted switching over between different winding taps of a regulating transformer, can be divided into two types. One, quick action tap changer employing resistive current limiting impedances, that is resistor type tap changers. Another is slow action tap changers using inductive, that is diverter type, or impedances reactor type for current limiting purpose, which also to be denoted as reactance type tap changers. However, most of the resistor type OLTCs are installed inside the transformer tank, in tank OLTCs, whereas reactor type OLTCs are to be installed in a separate compartment which is normally welded to the transformer tank. Switching principle in both the cases would have to follow the make before break contact concept. In both the cases, that is for slow action or quick action, that is resistor type and reactance type tap changers, both in case make before break contact concept. Now, see the diagram on load tap changer. By applying vacuum switches, okay. In OLTC, a resistor or reactor is used as a transition impedance, which may have to arrange of one or more units that would form bridge with adjacent taps for the purpose of transferring load from one tap to the other without interruption or appreciable change in load current. Transition impedance that would also limit the circulating current as produced during the period when both taps are in use. So far the United States of America network is concerned, the reactor type OLTCs are still be predominant, whereas the rest of the world have rather to shift over high-speed configured tap changers of using resistors for circulating current limitation during the tap transition. In India, also for power transformers 765, 400 kV and 400 kV to 765 to 400 kV and 400 kV to 220 kV, resistor type OLTCs are employed. Let's stop here. Further to be continued at later stage. Thank you for listening the video. Kindly do like, share, and subscribe my channel. Your subscriptions would encourage to post more videos. Also share your comments or feedbacks inside the dedicated comment section. If you have any suggestions or specific topic you want, then let me know in the comment section. Thank you. Thank you for patient hearing.